Assalamualaikum. What if I tell you the AI tools you are using today didn't start with code, but with a question? Can machine think? This video is for educational purpose, exploring the real history of artificial intelligence through documented events and breakthroughs. Over 100 years ago, scientists were already imagining thinking machines, but what followed wasn't success. It was failure, confusion, and decades of silence. AI rose, crashed, and nearly disappeared until one breakthrough changed everything. From a machine that could barely solve math problems to AI defeating world champions to tools that can write, speak, and create videos in seconds. This is the history of how human builds intelligence from nothing. And trust me, what happens next might surprise you. Let's begin.
Welcome to The Explainer. Okay, class is officially in session. Today, we're cracking open the lecture notes on the history of artificial intelligence. And it's a really fascinating story. You know, a tale driven by two totally competing ideas about how to build a thinking machine. One based on pure, clean logic, and the other, well, it's based on learning from experience, just like we do.
It all really kicks off with this one huge question. Can a machine think? I mean, back in the middle of the 20th century, when the very first electronic computers were just humming to life, the pioneers in this field, they started taking this question seriously. This wasn't science fiction anymore. It was becoming a legitimate engineering challenge. Could we actually create intelligence out of silicon and code?
And then comes the great Alan Turing. In his absolutely landmark 1950 paper, he just brilliantly sidesteps the whole philosophical trap. He said, you know what? Instead of trying to define a fuzzy word like thinking, let's just create a practical test. He called it the imitation game. Basically, could a machine fool a human into believing it was also human? And that simple idea right there, it shifted the entire conversation from abstract theory to real, hands-on practice.
All right, so settle in. For our lecture today, we're going to trace the pretty dramatic story of AI through these 5 key chapters. We'll start with that age of pure logic, see where that idea kind of hit a wall, and then we'll witness this quiet revolution that brought us all the way to the AI we know and use today.
So our story begins with this beautiful, almost poetic idea, the dream of reason. In this first age of AI, the whole goal was to teach a machine the rules of the game, and the game was human thought itself. The belief was, well, if we could just write down all the rules for logical thinking, we could literally program a machine to reason.
This whole approach is called symbolic AI, or as some people like to call it, good old-fashioned AI. And it was just so captivating because it felt really intuitive, right? It seemed to mirror how we thought, logically, step by step, in a predictable way. The goal was to build these systems that could reason from the top down, shuffling around symbols just like a mathematician proving a theorem on a blackboard.
And the absolute star of this era was a program called the Logic Theorist. Back in 1956, at the now famous Dartmouth workshop, where the term AI was coined, a lot of people showed up with ideas and theories. But Alan Newell, J.C. Shaw, and Herbert Simon, they brought a working AI. Their program could independently prove mathematical theorems. I mean, that was a truly stunning success.
Fast forward a decade, and this program named ELIZA showed that this symbolic approach wasn't just for math. By using some pretty clever pattern-matching rules, it could simulate a conversation with a therapist. And what's truly amazing is that a lot of users became absolutely convinced they were talking to a real person. It just showed how powerful even the illusion of intelligence could be.
But this elegant rule-based approach, well, it was about to run headfirst into a problem of its own making, a combinatorial explosion. And this wasn't really a failure of logic, not at all. It was a collision with the sheer, unpredictable messiness of the real world.
They called it the combinatorial explosion. Okay, think of it like this. You can write a set of rules for a game of chess. It's complicated for sure, but it's a closed system. But now, try to write the rules for just crossing a busy street. You have to account for cars, pedestrians, traffic lights, the weather, a stray dog. I mean, the number of possibilities just explodes exponentially. You realize you simply can't write a rule for every single thing. The real world, it turns out, is just way too chaotic. And this led to a period of pretty deep disillusionment. Over in the UK, a really critical 1973 paper called the Lighthill Report basically concluded that AI had completely failed to live up to its own grand promises. The result was a chilling effect on research funding, a period that we now call the very first AI winter.
The symbolic approach really hit its peak with chess computers, and you can see the brute force arms race right here. To finally beat a human world champion, IBM's Deep Blue in 1997 needed hundreds of specialized processors and the raw power to analyze 200 million chess positions every single second. It was an incredible feat of engineering, for sure, but it wasn't flexible. It wasn't actually learning.
But while the grand masters of logic were busy building these bigger and bigger chess machines, a completely different kind of thinking was quietly developing in the background. And this approach, it wasn't inspired by clean mathematics. It was inspired by that squishy, messy, and incredibly powerful computer inside our own heads, the human brain.
Now, what's really fascinating here is how it captures this total paradigm shift. Instead of that top-down approach where you program all the rules, neural networks use a bottom-up strategy. So you don't teach it the rules of what a cat is, you just show it thousands and thousands of pictures of cats, and you let it figure out the patterns for itself. It's a huge shift from logic to data.
And the groundwork for this, it was laid decades earlier. You had Marvin Minsky's first neural network computer way back in 1951, the perceptron in 57, and most importantly, the development of an algorithm called backpropagation. Now that was the key. It was what allowed a network to actually learn from its mistakes. But for a really long time, it was just an idea, waiting for its moment to shine.
So for decades, this whole neural network approach was kind of held back, just waiting. But by the 2010s, a perfect storm was brewing, and it was setting the stage for what many people now call the Big Bang of AI.
The breakthrough really rested on these three pillars. So first, the internet gave us big data, these massive training sets like ImageNet with millions of labeled images. Second, those old algorithms like backpropagation were refined for deep, multi-layered networks. And third, well, the video game industry gave us a secret weapon, graphics processing units, or GPUs. Turns out they were perfect for the kind of parallel number crunching that neural nets required.
The moment of ignition, the spark, came in 2012. A team led by Geoffrey Hinton submitted a deep neural network called AlexNet to the big ImageNet competition. And it didn't just win, it absolutely annihilated the competition. Its error rate was a massive leap forward, proving that this data-driven approach was now undeniably superior for these complex pattern recognition tasks.
And this really illustrates the impact, doesn't it? This wasn't just another small step forward, it was a total phase transition. That 2012 victory of AlexNet is widely considered the Big Bang that launched the modern deep learning-driven era of artificial intelligence.
So this brings us to our final chapter, our data-driven world. We're now living in the new paradigm that was created by that Big Bang. You could say the age of pure logic was over, and the age of learning machines had finally begun.
The line from AlexNet to the AI we have today is a direct one. The same fundamental data-first approach that allowed it to recognize images is the engine behind large language models like GPT that write essays, the generative models like DALL-E that create incredible art, and pretty much every other AI breakthrough you read about. It's all built on that very same foundation.
So this right here is the blueprint. It's the central dogma of modern AI. You take vast quantities of data, you feed it into very deep multi-layered neural networks, and then you run the whole thing on massively parallel hardware like GPUs. That's the recipe that has unlocked so much incredible progress.
And that brings our lecture to a close. We've seen AI's history as this amazing journey, moving from an age of pure logic to our current age of big data. So the final question for us all to ponder is, what comes next? Will we see a hybrid of both of these ideas, or is there another completely new way of thinking about to emerge? Class dismissed.